Good morning everyone. In the previous lecture, we designed a singly reinforced beam using the working stress method. We saw that singly reinforced sections are sufficient when the depth of the beam is adequate and the bending moment is within limits. Today, we move one step ahead and study the design of doubly reinforced beams. This lecture is very important because it explains why and when compression steel is required and how to design such sections using working stress method. This is lecture 7 of Design of RCC Structure. The topic for today is design of doubly reinforced beam using working stress method. By the end of this lecture, you should be able to understand the concept of doubly reinforced sections, know when such sections are required, and to perform a complete numerical design. A doubly reinforced section is a reinforced concrete section where a steel is provided on the tension side as well as on the compression side. Unlike singly reinforced section, here both concrete and steel resist compression. So this type of section is used when a singly reinforced section is not sufficient. Now let us understand why we need doubly reinforced section. Restrictions on beam dimensions. Sometimes beam depth cannot be increased due to architectural limitations or headroom requirements or floor to floor height restrictions. In such cases, additional moment is resisted by compression steel. Second is a reversal of bending moment. In structures like piles or water tank braces or chimneys, the bending moment may reverse. So both phases of the beam experience tension at different times. In case of continuous beams, the portion over intermediate support is subjected to negative bending moment, which requires compression steel. Hence, doubly reinforced section becomes essential. So figure shows a doubly reinforced rectangular beam where reinforcements are provided both in the tension zone as well as in the compression zone. Here AST represents the area of the steel in tension zone, whereas ASC represents the area of the steel in the compression zone. In working stress method, the design of doubly reinforced sections is based on equilibrium of moments. On the compression side, the moment is resisted by the concrete in compression and the compression steel, which will be converted into an equivalent concrete area. On the tension side, the moment is resisted by tensile steel only. So by equating the moment of resistance on the compression side and the tension side, we ensure the equilibrium of the section. That is what is explained here. So the moment of area on the compression side will be calculated using minus ASC x minus d dash plus 1.5 m ASC into x minus d dash. Whereas the moment of area on the tension side is m into AST2 into d minus x, where 1 minus m into AST is the equivalent concrete area in the compression side. Equating moment on both the sides will get the relationship for calculating the area of the steel required in the compression zone. In doubly reinforced sections, the total moment is divided into two parts. M1, which is the moment resisted by a balanced singly reinforced section, and M2 is the additional moment resisted by compression steel and the additional tension steel. So M is equal to M1 plus M2. This concept simplifies the design procedure. So the steel required for the moment of resistance for a balanced singly reinforced section, what we used for a singly reinforced section. AST1 is M1 divided by sigma ST into Z. Whereas the steel required for M2 will be calculated using the relation M2 divided by sigma ST into D minus D dash. So the total area of the tensile steel required is AST1 plus AST2. Now let us apply the theory to a numerical problem. Design a reinforced concrete beam simply supported over an effective span of 6 meter carrying a dead load of 10 kN per meter, live load of 12 kN per meter with a cross section 300 mm by 500 mm. The effective cover to the reinforcement on both the sides may be taken as 50 mm. Adopt N20 grade concrete and Fe415 H5ST bars. Note carefully, the beam dimensions are already fixed. Hence, if the bending moment exceeds capacity of a singly reinforced section, we must use doubly reinforced section. This is a classic and very important problem. As always, we'll start with calculating the design constants. The procedure, whatever we followed for the singly reinforced section, we followed the same thing, and the design constants, that is critical depth of neutral axis factor, lever arm factor, and the design constant has been calculated. Now let us calculate the total service load. So starts with the self weight, which will be calculated 0.3 by 0.5 by 25, which is the unit weight of the concrete. We'll be getting the self weight as 3.75 kN per meter. Adding all the loads, that is the dead load, live load, as well as the finishing load, we'll be getting the total service load as 26.75 kN per meter. Next, we can calculate and one more thing, we need to know that no load factors been used in the working stress method. Next, we can calculate the bending moment and shear force. For a simply supported beam with the UDL, the bending moment will be calculated as M is equal to WL square by 8 and shear force V is equal to WL by 2, which we are used in the singly reinforced section, where W is the total service load, L is the effective span. Substituting the values, we can calculate the maximum bending moment and the maximum shear force. We then check whether this moment exceeds the balanced moment capacity of a singly reinforced section. So the moment of resistance for a balanced singly reinforced section is calculated by using the relation QBD square, where Q is the design constant, B and D are the effective cross section areas. Substituting the values, we get the value as 55.53 kN meter, which is less than the maximum bending moment, which means that the moment of resistance for a balanced singly reinforced section is 55.53 kN meter. And the balanced moment M2 is M minus M1, that is 64.85 kN meter. So one thing we need to know in this case is, here the M, the maximum bending moment, exceeds the moment required for a balanced singly reinforced section, and hence this beam has to be designed as a doubly reinforced section. Now we design the tension reinforcements. So what is the step that is involved in designing the tension reinforcement is, first we need to calculate the steel required to resist the M1, and secondly we need to compute the steel required to resist M2, and we need to get the total steel required. So the final steel reinforcement provided must satisfy the permissible stress in steel as well as the equilibrium conditions. So with this, the steel required for M1 will be calculated using the relation M1 divided by sigma ST JD, which comes around 594 mm square. And the steel required for M2 will be computed as 705 mm square, and the total area of the steel required in the tension side is AST1 plus AST2, which comes around 1299 mm square. So using this one, we can assume some diameter of the bar Based on that one, we can calculate the number of bars required to satisfy this 1299 mm square. We are assuming a 25 mm dia bars, using which we will be providing 3 numbers of 25 mm dia bars as tension reinforcement, in which the AST provided will be 1473 mm square. Now we design the compression reinforcement. So here the key points is compression steel resists the additional moment M2. The equivalent concrete area concept will be used, and the stresses in compression steel to be kept within the permissible limit. So area of the compression reinforcement ASC will be calculated using this relationship, where M is the modular ratio, AST2 is the area of the steel required for satisfying the AST M2, D is the effective depth, X is the Liverham the neutral axis depth factor, and D dash is the cover required for the compression reinforcement. Substituting the values, the area of the steel required for compression zone is being calculated as 1977 mm square. Again, assuming the diameter of the bar, we can calculate the number of bars required to satisfy this 1977 mm square. So assuming 25 mm bars and 20 mm bars, a combination will provide 3 numbers of 25 mm bars and 2 numbers of 20 mm bars as a compression reinforcement, with the ASC provided as 2101 mm square. So this compression reinforcement improves the strength, the ductility, as well as the long-term performance of the beam. So as usual, after the flexural design, we need to check for the shear. So the steps involved in the design for shear is calculate the nominal shear stress, compare this with the permissible shear stress of concrete. Based on that, we can provide the stirrups if required. And this shear reinforcements is usually provided in the forms of vertical stirrups. So the procedure remains same. Nominal shear stress will be calculated. Then the percentage of the steel reinforcement, here the tension reinforcement alone will be considered and not the compression reinforcement. This will be calculated as 1.09%. Based on this value and the grade of concrete of M20 from table 23 of IS 456-2000, the permissible shear stress in concrete tau c will be calculated as 0.4 Newton per mm square. And this value is less than the nominal shear stress of 0.59 Newton per mm square. Hence, shear reinforcements are required. So the balance shear has to be calculated using the relation V minus tau c by PD. Again repeating, V is the total shear that will be acting on the section. Tau c BD is a combined the shear resisted by the concrete. Substituting the values, we'll get the balance shear as 26.25 kilonewton. So using again 2-legged 6 mm dia stirrups, the spacing of the vertical stirrups will be calculated using the relation ASV sigma SVD divided by VS as 220 mm. Now we can see this value is less than the allowable maximum spacing of 300 mm. Hence, provide 6 mm dia 2-legged stirrups at 220 mm centers up to quarter span length from the supports and gradually increase it to 300 mm centers towards the mid span. This is the cross section details. We can see we have a beam rectangular cross section of 300 mm by 500 mm with an effective depth of 450 mm. This has been reinforced with the 3 numbers of 25 mm dia bars as tension reinforcements and 3 numbers of 25 mm dia and 2 numbers of 20 mm dia bars as compression reinforcement, in addition to the 2-legged 6 mm dia stirrups at 220 mm centers as vertical stirrups. This completes the full design of a doubly reinforced beam using working stress method. So to summarize today's lecture, working stress method can be effectively used for beam design, and this doubly reinforced beams are required when the depth is restricted or moments are large. And the numerical problems are solved step by step using permissible stresses. In the next lecture, we'll move towards a limit state method design concepts. Thank you.